Hi, um, I'm I'm Demi Marie Obenauer, and I'm here to talk about protecting against persistently compromised devices, making compartmentalized operating systems live up to their promises. I'll start with an introduction, then I'll describe the attack, how to defend against it, what trust when it comes to devices is, and finally conclusion. So device pass-through. Why do we use it? Well, it's the only way to isolate drivers. And it's believed to be secure if it's properly implemented, at least until the system reboots. The problem is that real devices are stateful. Some of that state may be persistent across reboots, like option ROMs, device firmware, or intentional storage that's part of the device function. And even when it's not persistent, there's no guarantee a reset clears it. Attackers can exploit this. So how does the attack work? Well, first you compromise the VM with an attached device. Then you compromise the device itself, or you trick it into doing something late after the CPU's reset. And then you wait for the host to reset. And then you exploit the system when it boots up. The consequences are, in the Cube's case, I'm using Cubes as an example, because the most people here are going to know, it would be a sysUSB to DOM0 or sysnet to DOM0 breakout if you're using things that aren't the integrated or chipset device, and if someone can come up with an exploit, of which I am not aware of one. It also means GPU pass-through isn't secure, and while I'm not aware of a specific exploit there, I'm aware of something pretty close. People have tampered with NVIDIA GPU vBIOSes before. And storage pass-through, quite likely, isn't secure unless you trust the storage vendor's firmware. So why does this work? Well, some devices like GPUs need option ROMs to initialize. Device drivers are vulnerable to malicious PCI devices. They consider the device trusted, which is one of the many problems with Linux, but that's another story. And most importantly, the operating system and likely the firmware trust that devices are what they claim to be. And without fixing that, the rest of none of the other stuff really matters. So how do hyperscalers solve this? They use custom hardware, cloud custom board designs. They might either completely emulate the flash using an on-chip microcontroller or put an interposer there. And that way they can wipe out any persistent mutable state during a device power cycle. And an onboard microcontroller makes sure that everything is sequenced correctly so that when the CPU is reset and comes up, all the devices are back in a trusted state. But the rest of us don't have that option. It is possible to provide some security even on stock hardware, though, if you're willing to accept that persistent compromise might happen and instead design the system to limit its impact. That means that users need to be able to safely use a device, even if one or more of the devices is permanently attacker controlled. The root thing that makes that so hard is that the firmware and OS do not know which devices to trust. On a server, you can use the SEV-SMP TDX approach of trust nothing, but that doesn't work for a desktop because to a user, the system isn't the CPU or the GPU. It's the keyboard, the mouse, the microphone, the speaker, and the display. It's the system's, more generally, it's the system's sensors and effectors. The things that the computer can use to receive input from the outside world and do things to the outside world. These devices, however, the ones that are actually those, let's assume they're trusted, because if they are assigned to an untrusted entity, that untrusted entity can already do bad things by tricking the user or receiving data from the user. Only things that are passed through have to be assumed potentially compromised. So most devices don't have a cryptographic identity. A device can pretend to be anything else, but there's one thing a device can't do, and that is physically unplug itself and move itself and then plug itself somewhere else. It can't do that. So it can't pretend to be plugged into a different slot. So if a device might be compromised, quarantine the slot that it's in. So what's a quarantine slot? It's meant to be a safe place for your untrusted devices. So a slot you might want to quarantine might be slots that ship from the factory with nothing in them, or slots that the OS has told the firmware to quarantine via UEFI variables. If DRTM is in use, UEFI runtime services aren't available. A signed file on the EFI system partition that's included in a TPM measurement could be another option. If a device is behind a quarantined slot, then you forcibly assign it. Then it's to a driver that can handle that. For ZenDOM 0, it'd be Zen PCI back, or VFIO, or otherwise for VFIO PCI. Because the assumption is not you don't want to use the device at all, otherwise you just disable the slot entirely. It's you want to pass it through to something that you also don't want to have to put trust in. Since the busmaster enable bit on the quarantine slot is initially cleared, it can't perform DMA until the IOMMU is set up, so DMA attacks from these things don't work. Why this route? Simple. I previously, in an earlier talk a bit over a year ago, proposed a version with a complex device trust scheme, but that's harder to implement. Budget's limited, go with the simplest option. Conclusion is that persistent compromise is a significant threat to compartmentalized operating system via device, but thankfully firmware and OS updates can solve the problem. So let's start working on them.